Cool. So let me introduce Sayak. Sayak is a research engineer at Hugging Face working on diffusion models. His day-to-day work includes maintaining the diffusers library, which a lot of us use, and training diffusion models. He's also leading collaborative applied research efforts. He co-invented Sprite and Maple to improve spatial consistency and preference alignment on diffusion models. Let's welcome Sayak. Sayak, take it away.
Yeah, thank you. Uh, I hope I do not run this over, but I think I've put in a lot of sugar and sweet while preparing the slides, and I hope the folks working in this area will be able to resonate with this. And I hope this is a really relevant area where I could harp on a bit. So yeah, I'll just get started right away. I hope there will be some time for Q&A. But if not, I think we are recording this and folks can always reach out to me. I'm pretty open to those things. I think we have a shared Slack channel on our workspace, so we can always talk offline. But yeah, let's get started. Couple of disclaimers for the folks that are watching this or will watch this later. This talk is definitely not an exhaustive overview of all possible methods. So if you feel like a method that you really wanted to see in this talk is not here, sadly, know that that's an honest mistake, or I probably couldn't figure a way out to include it in the most salient way possible. And then this talk is more about controllability. So if you find things like transfusion or more exotic architectures missing, or more exotic training objectives missing, that's intentional. And then this talk is going to be a mixed bag. So you may see things that are pretty well known in the community, and there will be some opinionated takes as well. So just know that this is going to be a mixed bag of things. There might be things that are probably from 2022 but still are very much relevant as far as the community goes, because one of the perks that I get to have as a maintainer of diffuser is like really listen to the community that are making things work. So I'll present those things as well, and then I'll share the slides after the talk. And as mentioned, I'm always happy to chat about the things I may have missed out on, so that I can also improve. I just wanted to keep things high level and then sort of develop a more coarse to fine grained way of tackling things. So yeah, a couple of favorite flashes from the recent set of text to image models. Pixar Alpha is fairly old at this point in time, but I still like the picture, that famous Imagine picture. But my most favorite one is this tiny baby astronaut hatching from an egg, which is from Flux. Actually, it's not from any of the official releases of Flux. I decided to merge the Schnell and Dev variants of Flux to save some time. So yeah, I think it's pretty spectacular. And I also wanted to go over some boring things, just a couple, just 2 slides, so that we have some context. And like I just wanted to introduce what diffusion models are, but quickly, of course, I won't be able to go over the gory details in a matter of 50 minutes. So I like to think about diffusion as a process of gradually refining a noise vector so that it becomes a realistic image. And the sequential or the iterative nature of this process is, I think, very important to take note of, because unlike GANs, it's not one shot, it's iterative, which is why there's a lot of interesting research around time step distillation around diffusion models. But yeah, long story cut short, I like to think of diffusion as some sort of process of refining a noise vector gradually, taking infinitesimal steps towards the data distribution. And of course, when we condition this some kind of denoising process with text, we get cute creatures like this. But it's funny, these models have this uncanny ability of being able to associate objects that are present within our prompts and give them coherent and structural forms, which is pretty elevating in my opinion. And then, honestly speaking, going from text to a hyper realistic image is already elevating enough, because there have been studies showing that it really does help many artists. I think OpenAI put together a study about this, The idea is to be able to aid artists of all forms with this kind of visual systems. So that's why I also feel and I resonate with the fact that the ability to do generate images from text is already pretty elevating enough. But then why go further in the first place? So that's why I wanted to spend a couple of minutes to motivate the need for controllability in diffusion models. So I want the model to respect the prompts. For example, if I ask an object of certain attributes, I want the system to bind those attributes to those objects. And this is one of the many problems. But long story cut short, I want the system to basically respect my prompt and not generate anything that I'm not expecting in that prompt. And then I want to be able to render my favorite pets in the final image. Maybe I have a cute dog that I want to render in interesting contexts, maybe in front of Eiffel Tower or whatnot. So I want to be able to have some kind of subject-driven properties in the generation process. And then I want to be able to generate with a specific style, maybe manga kind of style, or maybe some neopop kind of style. And then not just text, I want the system to also follow pose, maybe, or maybe a depth map. So I want to be able to use additional conditions alongside the prompts, because language supervision, as I will keep mentioning, is definitely elevating enough, but it can be vague at times. So guiding the entire generation process with some visual cues to ground the generation process with some visual cues is often very helpful. And then this entire framework of using additional visual cues can be used to do image to image synthesis. We can incorporate auxiliary conditions, like I mentioned, pose, depth map, and so on. And then we could also extend this framework to do image editing with with language supervision. I mean, imagine doing Adobe Photoshop kind of stuff, but with language, natural language instructions, which I think is very, very, very powerful. And then ultimately, I want to be able to generate with improved fidelity across the board, maybe better aesthetics, for example. So yeah. So for the next couple slides, I'll present a couple of approaches, and which I believe will be general, because we have got many classes of diffusion models, broadly pixel space and latent space. But the approaches I'm gonna discuss today will be fairly generic, and they will be applicable to both pixel space and latent space diffusion models for the most part, until and unless explicitly specified. So yeah. And this is roughly going to be the theme and the structure of this talk. I'm going to pick some of the limitations that I think are prevalent and worth solving for. And then I'm going to present some solutions. Some of them will be well known, have been like well adopted by the community, and some of them are going to be a bit more opinionated. And I'm also going to leave some further readings in case it piques your interest. So, yeah. And this is going to be part one, where we discuss the problem of subject driven generation, which we can further extend to do personalization. Like as I was mentioning, maybe I want to render my cute cat in some interesting contexts, basically concepts that are very new to a pre-trained diffusion model. And thereby I also want to introduce personalization, and I think this is incredibly useful for many entertainment and content industries. So yeah. So basically, we want to be able to embed a new subject in the output domain of a pre-trained model. So we want to be able to figure a way out to do fine tuning so that the model adapts itself to this new output space, but without also incurring something like catastrophic forgetting. For example, if I want to generate images with my cute dog, I don't want the model to forget what it had learned during its pre-training, costly pre-training, albeit. So and also the idea is to do this fine-tuning process fairly quickly. Like it should not take 1,000 images for the model to quickly adapt to this new set of images. So that's the idea. Basically, our expectations are the following. We want to be able to quickly adapt the output space of our pre-trained model, basically maybe ideally with 3 or 5 images, but 10 15 images also just tend to perform better. And then during inference, we just want things to work out of the box. So where do we start? So we take a pre-trained model, and then we put together a very little data set, training data set, ideally with 3 or 5 images, but it also depends on the difficulty of the concept a bit. So maybe the range would be, an ideal range would be somewhere in between 5 to 50, 50. And then we also want to put together the data set such that the model is able to pick up on some trigger words. And how do we do those trigger words? And it could be as simple as a unique identifier like we are seeing here, maybe v within square brackets. But I will have some more pointers on this in a couple more slides. But just for the time being, just know this: we have our training data set, which is like 3 or 5 images of cute dogs, for example, and they will all be mapped to a single caption. Again, it will be revisited in a couple more slides, but for the sake of simplicity, let's just proceed with this. And all of the 3 to 5 images will have the same caption containing a unique identifier, as simple as v within square brackets. And within inference, after the training is done, we want to be able to render our cute dog in the final generated image. And while doing so, we want to be able to append that unique identifier in our prompts. So yeah, and diving deep a bit, we want to establish some notations here, because that will help me to further dive into the objective of dream booth. So without the loss of generality, we start from the original image. It can be latent if we are dealing with latent space models. So X we have, and then we will gradually add noise according to a particular noise schedule. So the noise will be added with respect to the current time step, and then we will have a couple of controlling factors which are dependent on the noise schedule that we are using. And then we will have our conditioning vector. In this case, since we are doing text to image, this will be text embeddings. And then we will have the diffusion model that we want to fine tune, right? And this objective that we are seeing here is also known as the epsilon prediction objective, because we want the model to predict the amount of noise that we added during the forward diffusion step. And the idea of dream booth is really simple. So dream booth introduces this concept of prior preservation loss. So we want to be able to do the fine tuning using the regular epsilon prediction objective. But since we also don't want the model to forget its pre-learned concepts, we want to also regularize the training with what they call or refer to as prior preservation loss, where you take the same prompt but without the identifier. You take that prompt and then you generate a bunch of images, typically 200 to 300, and then you apply the same process, but you keep the pre-trained model frozen, and then you take a weighted combination of both the losses, and then you have your prior preservation loss. Sorry, was there a question? I guess not. All right. So yeah, that's the idea of prior preservation. But yeah, I'll get to the but let's first describe, let's first demonstrate and showcase a couple of interesting results here. So we wanted to do subject driven rendition. That's all, butterflies and shiny. We are able to generate this cute dog in front of interesting things. That's one. But it also caters to multiple use cases. For example, art rendition. If my training images were like this, I'm able to generate that cute same dog in interesting renditions of art. For example, Leonardo da Vinci, for example, or even Michelangelo, which is pretty intriguing. And then I can also modify the properties. Like I could give this dog an appearance of a bear or a panda or a koala, which I think is pretty cool. But a bag of learnings here. Dream Booth, for your information, was proposed in the context of pixel space models. But all of these findings are from the latent space model, because Dream Booth code was never open sourced, right? So with as we found out, again, these are opinions. Feel free to try these things out yourself. With modern models like Flask, prior preservation isn't often needed. Of course, it depends on the difficulty of the concept that we want to learn. But typically, for the most part, prior preservation isn't really needed, and thereby we can cut down the training cost quite a bit. And the use of unique identifier is also optional. Just a simple trigger word often suffices. And then, different captions. We mentioned that all our training images will probably, get mapped to a single caption having that trigger word, but different captions having that same trigger word, as opposed to using the same caption per training image, can be helpful, especially if the subjects within the training images are present in varied conditions. And then no one really uses full fine tuning for dream booth. Usually parameter efficient fine tuning with something like LoRa, it just almost always works. And there's a whole bag of other tips and tricks that we have enlisted in this little blog post, which of course I'm gonna be sharing my slides, and you can check them out later. And if you really want to see how far we can push the extremes with dream booth, I think you should really check out the studio. There are all kinds of dream booth fine tunes, like to control motions. You could go back in time and things like that. I think it's pretty spectacular. So yeah. And then here are some further reads. Let's say you do not want to put together 3 or 5 or even 10 images. You want the model to learn from just a single image. Then BLoRa, I invite you to check out BLoRa. And you probably do not want to even do fine tuning, and then you could probably do zero shot subject driven generation, but quality takes a hit there. But yeah, the idea is pretty intriguing in my opinion, so you could check out Diffusion. And the hottest kid on the block would be pivotal tuning, where we combine textual inversion and dream booth. And pivotal tuning typically works best when the concept that we are trying to teach the model about is very complex in nature, or it's utterly new. So, and pivotal tuning just works better. Of course, there's a training cost, there's an increase in the training cost, but it typically works better. So, and yeah, I think I'm doing okay on time. So I'm not gonna stop for question and answers. I think we can do that later at the end of this talk if there's time. So I'm just gonna proceed to the next set of limitations and solutions. There will be 4 such parts, and we are in the second part. So yeah, and probably this is the densest part. So I'm excited and equally nervous. So as I was mentioning during the at the beginning of my talk, is what if we wanted to condition the generation process, let's say on a pose image alongside language supervision of because language supervision is definitely interesting and elevating and all that, but it can also be vague at times. Like, how do you precisely describe an image? It's very subjective in nature, but pose, it's probably more objective than that, right? So basically, here's an example. I want Darth Vader to dance in a desert, but I also want Darth Vader to follow this particular pose. So how do we do that? So ControlNets are a very powerful framework that allows us to basically extend conditionings to different sets of visual cues, and it's a very flexible and powerful framework, I would like to believe. So ControlNet is basically an auxiliary module which is initialized from the denoiser that we are using, but it's like a partial copy of the denoiser which we eventually train on our custom data set. And it's initialized from the weights of our pre-trained weights of our denoiser. And we also add a couple of zero convolution blocks so that the adaptation process is not very aggressive, so that it does not hamper all the pre-trained weights too drastically. Again, very good old classic fine-tuning trick. And that's basically it. The ControlNet structure, structurally and architecturally speaking, it's very similar to the denoiser that we will have in hand. For example, for UNet, the ControlNet structure will be different. For recent class of transformer models, the ones that we see in Flux, the ControlNet structure will be different. But the general idea is to keep the structure as close to the denoiser structure as possible. So yeah, but there are some guiding principles, such as we want the extra added blocks to be initialized to 0, so that the adaptation process is not as drastic. And the training objective remains the same. Of course, it depends on the original pre-training objective a bit. For example, if your pre-trained model was trained using something like rectified flow, this training objective would change. But for the sake of simplicity, let's say we had our pre-training using epsilon prediction, and in that case, the ControlNet fine-tuning, the ControlNet adaptation process will follow something similar. But in this case, we will also additionally condition with some kind of image embeddings computed from the ControlNet module, and then we backprop through the ControlNet module using this objective. And again, it's a very powerful framework. It's not just limited to poses or lineages. You can do all sorts of stuff like sketch, human pose. You can do segmentation. You can also condition with lineage filters and so on. And also there's this recent class of control nets which are called union control nets, which can take multiple such conditions and still give you very realistic looking outputs. And as I was saying, shall I say controls, because it's possible to combine these multiple conditions. But of course, for this case you would need two such differently conditioned control nets, which kind of increases the inference cost a bit. But there's this union control net that lets you combine this different multiple conditions without having to increase your number of networks. And yeah, on the right hand side we can see our giant is able to follow both these visual cues and do well. And we can actually extend this to a video, very short animation like video. So yeah, this is me digressing from the talk a bit, but I wanted to show this very cool example that this framework called text to video 0, which lets us take any 2D pre-trained text to image model and extend them to become text to video ones, albeit for a very short number of frames. But I think this is pretty cool. So yeah. So now I wanted to take a step back and give you some ideas about what it would take to develop more generic image level prompting, because till now we are considering images as some sort of separate conditions, but we want that to be more general so that we can consider images as some kind of mere prompts, just like we do with text, right? And some of the problems with the existing frameworks like ControlNets is like they require separate training on custom datasets, and often it can be quite cumbersome to put together a custom dataset and then do training. And with modern large models like Flask, it can be quite cost expensive. And then we want to be able to do more generic image level prompting alongside text prompting, like I mentioned. And then some of the needs that we want to have here is a strong image level encoder to develop representations of the image prompt, just like we do for text prompts. And then we want to be able to teach a pre-trained diffusion model to process and make sense out of those image representations computed from the image encoder. And some expectations here are it should be plug and play. Like we should be able to take a pre-trained diffusion model or its fine-tuned copies, and then we should be able to plug and play plug basically we want to be able to plug that module into the pre-trained model or its variants like fine tunes and just be done with them, as I was mentioning. And then it should the said module should also be compatible with existing auxiliary modules such as ControlNet or even LoRa and so on. So how do we do such things? Of course, it's clear that we need a strong image encoder, and it's common to use the text tower of clip. I know we have fancier text encoders like T5 or more recently Gemma 5.3 and so on, but let's for the sake of simplicity, let's consider and get back to our good old clip. It's common to use the text tower of clip, but the image tower is largely underexplored. So we could readily leverage the pre-trained image tower of clip to consider as our image encoder. Then we also want to connect the image representations with a small projection module so that the dimensions match. And then we also want to decouple cross attention, and let me harp here on a bit. So our common practice is to do cross attention between text features and the newly computed image features, where the cross attention layers in the pre-trained diffusion model are typically kept frozen. So what many studies have found out that this basically prohibits effective integration of the image features. So we need to find a better way, and it could be as simple as just adding a new cross attention layer for each existing cross attention layer within our pre-trained network. And then we basically want to train the projection module that we added, which is just a couple of layers, and the new cross attention layers that we added, which in combination could only lead to just 22 million parameters, which I think is fairly small. And then this kind of decoupling, this kind of decoupling of the cross attention layer can only be possible with models, of course, that have cross attention SDXL, because modern diffusion models, they don't have cross attention, they have something called joint attention. So these design choices need to be revisited, but the idea largely stays the same. We want to be able to decouple the attention where we have connections between different modalities, for example the text and the image features. And here's how the regular cross attention in diffusion models look like. So we have got queries coming from the image latents, basically the latents that we are starting off with during our generation process, and then we have the text features as our keys and values, and W's are basically the projection weight matrices involved in the attention process. And then if we want to decouple this entire cross attention thing, we basically want to add a separate cross attention module for each existing cross attention module that takes care of separately attending to the newly added image features as well. And that's exactly what we see here on the right hand side. So our queries are now the latents computed from the image prompts, image level prompts, and rest of the process still remains the same. And only the weights belonging to the query are the newly added weight matrices, and rest of them are basically the same. So yeah. And yeah, just a small correction here. So since we are decoupling the cross attention parts, the projection weight matrices belonging to the keys and the values will also need to be updated. But in order to accelerate convergence, we initialize them from our existing cross attention layers, and then we sort of learn them during the training process. So yeah. And this is how the pictorial representation of IP adapter, so that was IP adapter, by the way, this is how it looks like. So we can see most of the modules here are frozen, and we only have a linear layer and a layer norm layer as our projection module. The image features are then computed, and we have a newly added cross attention layer per existing cross attention layer from our pre-trained module, and that's basically it. So here's how it looks like. So during training, again, the training objective will vary depending on the model that we are using. But given that we are using epsilon prediction, we are just appending the image level features here. So yeah. And then during inference, we can basically control how much we want the image features to contribute to the generation process, which I think is pretty cool. And then image prompting with a base model, maybe we wanted to prompt with Einstein's image and then have like a prompt like this. And it's possible to do things like this. Basically, some sort of a rough extension of Dreamboot, I would like to believe. And then we can actually do image prompting with fine-tuned models. So realistic model and the anime model, they were all fine-tuned. They are all fine-tuned version of Stable Diffusion v1.5. So yeah. And on the left hand side we have our image prompt, and then yeah, and we can do all sorts of existing tasks like in painting, image to image synthesis, and so on. And then we can also combine IP adapters with control nets, as I was mentioning. So that's pretty cool. Yeah, we have detailed about all of this in a very extensive guide that we have in diffusers, so feel free to check it out if this is interesting. And then I also want to take this opportunity to motivate the need to have an any-to image synthesis paradigm. Like language models often have this, image, video, or text-to-text paradigm where we prompt the language model with something like text, and then we want to have want to text as some kind of text as output. And the benefits of doing this is it has shown multitask transfer, cross-modal transfer, and then in context learning, which is pretty cool. And then my humble ask is that can we do something similar to generative image models? So regular text to image generation, with capabilities for subject drivenness, structural control, but we also want the basic text to image generation properties to be in there with that single model. And then we want that same model to also solve multiple computer vision tasks, such as denoising, deblurring, basically some kind of image to image task. And then we also want the model to have in-context learning. Some questions would be, how do we create such a data mixture in the first place? And what architectures to use? And how do we, learn new tasks quickly? How do we, induce the concept of, task embedding, for example? Now, I want you folks to think about that. There's already an existing framework for that, but let me present some results. It already exists. So same model that can do deblurring and detection of skeletons in the form of poses. The same model can also do some kind of style transfer. And then I encourage you to check this paper out. It's called OmniGen, which kind of gives you this any to image synthesis paradigm. But there are many problems that are still underexplored, like what's the impact of task mixtures, how well do we generalize to new tasks, how do we learn new tasks quickly, and so on. So yeah, all these works are pretty cool. I think it started off with instruct pix to pix, SD edit, and works like those, and then EMU edit took it up a notch further, and OmniGen is pretty cool. So yeah. And here I am, my second last set of limitations and solutions. So yeah, let's get cracking. So this problem refers to catastrophic neglect and incorrect attribute binding. The problem is in this image, I prompted the model with a yellow ball and a blue cat. It basically neglects one or more objects in the generation. And then I've got the problem of attribute binding, where the model fails to properly bind attributes to objects. So this is bad. This is not at all expected. So what do we do? So first, let's try to understand why this happens. So the major problem is within the poor captions, typically seen in web crawl datasets. And here I present a couple of examples from the Lion dataset. As we can see, the prompts are way off. So yeah, it doesn't help. And recap basically provides a really easy way out of this. So we train an image captioner on a manually curated data set. So now we have a specialized image captioning model, and then we recaption our existing data set, and then we fine tune a pre-trained model on a 50-50 split between the synthetic captions and the original captions. Because if every time a user has to write a very long caption, that's probably not a good user experience. So we want the model to also retain its short prompt following abilities. So yeah, this is basically it. So we use the specialized image captioner to generate two kinds of captions. One is short, another one is long. And then we sample long and short captions with a 50-50 chance during the fine tuning process. So as simple as that, and the results are quite remarkable. So yeah. And principled captioning approaches like this, it can also improve spatial consistency, because if I want the model to generate something on top of something, I want it to be there. I want the final generated image to reflect that. And as it so happens that the existing captions within the web crawl datasets, they do not respect any kind of spatial order of things. And it turns out that if we can generate captions that have spatial focus, it can largely help. So and tasks like this, having spatial consistency in the systems are very crucial, especially for things like robotic perception. So yeah. And of course you all have been thinking, but these techniques are still need fine tuning, which is expensive, and I want to keep things as training free as possible. So what do we do? And yeah, let me take this opportunity to present Tony's work. Tony, please forgive me if I'm doing something wrong here. But yeah, I really like LLM grounded diffusion, so I had to pick this one up. So user prompts, as we saw, don't contain precise information about object location. So of course, as a consequence of that, they lack grounding in case of complex relationships. Now the question becomes, how can we augment the generation process to be more grounded? Now LLM grounded diffusion solves this by decomposing the entire generation process into multiple stages. it first leverages a language model to obtain a layout, which is basically a principled, captioned object coordinates, and then it takes those layouts and parses them and guides the generation process so that our generation process is grounded in the layout that was generated with the LLM, and it does not incur any training, so we are good. Now, as I mentioned, it's a two-stage process. First, we need to be able to generate the layout so that we could ground the generation process with the layout, and it's typically done by an LLM with the help of in-context learning, of course. And what do we need? What do we need to control such layouts with an LLM? Of course, we need a prompt. We first specify the broad task we want to achieve, and then we provide additional details about the tasks. For example, it's an image generation task, so we want the language model to know about it. And then we provide in-context examples, and then our expectation is that the language model would just follow those and complete whatever we ask it to. So yeah. And then some guiding principles include, we only want to, we want to take all the instances of the foreground objects, and we want to enforce the language model to generate one bounding box for sure per each of those object instances. And then we want to also ensure there are no foreground objects specified in the background prompt, because we want that to be controlled by the diffusion process, because that's where it specializes in. And the stage 2 is where all the fun begins, where we want the we want to ground the diffusion process with this layout. Now, how do we, some immediate questions are, how do we incorporate this layout? Because naive regional controls through some kind of cross attention manipulation, they lead to suboptimal results, because instance level control is not that discriminative, it's not that powerful with the existing approaches, because the instances of the same object aren't that discriminative in the latent space, considering we are doing latent space diffusion models. And with the two-stage generation process, what we do is we first generate the mask latents for each object instances, only one object at a time. That's exactly why we want the LLM to generate only one set of coordinates per object instance. And then we want to be able to find a way to compose all those mask latents and then use it to guide the diffusion process as a prior. Again, some questions here. How do we ensure each foreground object is placed in the designated box? I guess that's the meat of the entire discovery, right? And as it finds out that we can solve this by treating this as a mini on the fly optimization problem, we can minimize an energy function here. And I welcome you to check out all the details in the paper, because I don't think I can do a justice here within this short period of time. But yeah, I think LMD actually solves a whole lot of problems that we discussed up till this point in time. Like spatial reasoning, we used a whole data set, like a billion scale data set to solve this, but LMD can solve it without doing any training apparently, so that's good. Then we can solve the problems of negation and numeracy, which are very apparent problems in existing diffusion models. Again, LMD rocks. And then multi-turn image editing, my holy god. I mean, image editing of course needs training, but yeah, again, LMD comes to the rescue, which is pretty cool, pretty cool. Again, I can't help but emphasize on the fact that all this but training free. Of course, there's a cost when we are doing on the fly little optimization when we are doing inference, but I'm sure we can figure out some clever engineering tricks to further optimize it. So yeah. And yeah, I welcome you to also check out LMD for videos, LVD, and I also encourage Tony to open source the code if it's not already done. And Glygen, it's open source. It's open source. Yes. Oh, cool. I referred to your website, but it said it's yet to be open source, so I'll update that.
Okay, I'll change the website. It was open source a long time ago.
Cool. And Glygen, I think one of the first works to do any grounding related work for diffusion models, grounding with an open set vocab, which was pretty seminal when it came out. So yeah, pretty cool set of work. And my final part is probably the simplest one, but I think is also very important. And I also want to give some of the opinions about some of the future research directions here. So the final part. So yeah, of course, an obvious one, my image doesn't look as expected. Of course, language supervision can be vague, as we have been discussing. So a cat, right? This was the prompt, by the way. So where is photorealism? This is just a water painting. I mean, I wanted better than this. I wanted the cat to apparently yawn and basking in the sun, not doing it. I wanted to look more aesthetic. Of course, a never-ending user ask. And then I wanted the cat to have sleepy eyes. I don't know. None of those things are present here. So what can I do here? Well, start by improving prompting, of course. Some of the guiding principles to keep in mind here is, what's the image medium? How do you want the final image to look like? Is it a photo? Is it a painting, 3D illustration, or what is it? Because I know this can be limiting, especially for models that use small text encoders like Clip, only 77 token length. But of course, with modern diffusion models such as Flask, you have T5, which has like a much larger token length, which is 512. So be sure to take advantage of that. And then what is the image subject? Is it a person? Is it an animal? Do you want the cat to look like a, I don't know, dog or a tiger? Be sure to specify it. And then what details would you like to see in the image? And then this becomes particularly useful, as I was mentioning, when the underlying diffusion model supports longer prompts, Stable Diffusion 3, Flask, Pixar Sigma, for example. And then we can actually control image medium by improving prompting, such as this. Let's say we are starting with a very short prompt, a cat with a tiger-like look, realistic, and this is how it looks like. But I also wanted the image to have a certain cinematic vibe, basically like this, which apparently looks more pleasing and more aesthetic. How do we do that? So that's it. We follow some guidelines. We basically upsample this caption to that aligns with my expectations, and we of course take advantage of classifier free guidance by also appending a negative prompt so that my diffusion model does not lead to a stray. So yeah, all of these are templates borrowed from a work called Focus from the ControlNet author, and you can do all sorts of stuff here. Like this was my original tiger like cat, and then I have it rendered in different forms: cinematic, 3D model, neopunk, and so on. And as I was mentioning, these are all following a particular prompt template, and the expansion list is provided in Focus, which I think is pretty like a free lunch kind of a stuff. So pretty cool. But this is tedious, of course. Like figuring out the exact keywords, I mean, this is tedious. No, we can't do it. I mean, how can we automate this? As it turns out, again, you were probably expecting this already, but we can actually do a pretty good job of this by using a very small language model, something like a GPT-2. And here's I want to do. I want this banana shaped couch in my living room to look a bit more charming of sorts. So yeah, and this is roughly how the workflow looks like. We want to be able to manually curate a prompt, but we do not want to be manually curating a prompt because this is time consuming. And instead we want to leverage an off-the-shelf pre-trained model to automatically enrich or upsample a prompt with additional important keywords, which I'm sure we can have a list of. And then we want to curate that list of keywords and force GPT-2 to generate those words to enhance the original prompt. Maybe an example would be a cat, to go from a cat to all the way up to a very detailed prompt of what we actually want to see, not just a cat. And this is how it would look like. So yeah, I can see now it's basking, it's about to yawn, and it also has sleepy eyes. It's all good. And I think I was trying to build up to this moment, inference time scaling, and the emoji here is very significant and probably the most important part of my slides. So we have been doing inference time scaling for diffusion models, I think unknowingly. Probably the studies did not talk about it enough, but the idea here is to allocate more compute during inference to focus on specific things. maybe image prompt alignment, better aesthetics, better preference alignment, for example. So here's how a workflow would look like for doing inference time scaling. Maybe we want to optimize for more image prompt alignment, but in a multi-turn setting. We first obtain an image from our prompt, then we leverage an off-the-shelf reward scorer. In this case, it would be clip scorer. If the score is okay, we are good. If the score is not okay, then we use an LLM to modify the prompt, and then we sort of repeat the process. So and this in this process, while prompting to the LLM, we also incorporate the previous prompt, and we also incorporate the clip score, and maybe we could also incorporate the generated image if we can afford the computation cost. And it could be extended to multi-reward settings with multiple scores as well. And then an immediate question would become like, how do we lower the compute without compromising quality? And of course, there's a trade-off to be had in between fine-tuning and inference time scaling. Maybe we create a very small synthetic and high-quality dataset following the workflow that I demonstrated, and then we fine-tune an existing model and just see what happens. And of course, there's like two recent works in this area. One is from Confusion, from the authors of Textual Inversion, where they try to find out or search for highly optimized Comfy UI workflows with a language model. I think is pretty cool. So yeah, but yeah, I mean caption upsampling is here to stay, so definitely worth looking out for it. And I couldn't mention this set of techniques in my talk, but I would definitely encourage you to check out all the guidance related shenanigans. For example, perturbed attention guidance is, I think, definitely worth checking out. And it's also worth thinking about how can we rethink the guidance process, because it effectively doubles the batch size and thereby increasing the compute costs. And there's a lot to be discovered about guidance, and I think Karas et al. Already did a pretty good job in their auto guidance paper. But I think we really need a paper themed around rethinking and characterizing guidance and improving guidance in that process. So yeah, definitely worth thinking about these things. So yeah, I think that's about it. I didn't get in time to talk about preference alignment, but I have included a couple of works that I think are pretty interesting. So yeah, feel free to check them out. But yeah, I think I ended right on time. Wow. But yeah, I think we have 2-3 minutes for questions and answers. And I'll also share the slides with Tony so that we can distribute it. So yeah, that's it.
Thank you, Sayak. Anyone has any questions for Sayak? And also, tomorrow we'll have some slots for one-on-ones with Sayak. If you're interested in any of these works, or interested in chatting about the diffuser related stuff, you're free to sign up. It's in the Google Sheets.
I had actually kind of a technical question about model fine-tuning or LoRa fine-tuning, especially comparing Flux versus SCXL, as you kind of mentioned. How do you think the hyperparameters are different between fine-tuning these two different models, and why do you think they're different? So you mentioned that for Flux, you don't necessarily need to do prior preservation when doing personalization.
Yeah, definitely. So one is Flux is definitely objectively better, but that's something we already know. That's a very boring point. Second is architecturally they're quite different. If we only focus on attention, the attention mechanism is different. SDXL has cross attention and Flask has joint attention, which makes many things very different. Like if we want to blindly apply the original LoRa, how do we go about choosing our query keys and values? Like, do we only target a particular branch in the joint attention architecture? Do we co-optimize them? Several design choices are needed to be considered. So that's one. And then as you keep increasing your rank while you are doing LoRa, and since Flux is already like 12.5 billion, you typically incur a lot of training costs. So how do we target just the layer for the given concept at hand and sort of get away with good results. That's how I like to think about it.
Cool. It's the time. If you don't have any questions, let's thank Zach again. And I'll definitely post the link to the slides and also the link to the recording